Hi, everyone. Welcome to the seminar. I'm happy to introduce Ahmed Abdi, who seems to know a lot of people already because he did a PhD here in Waterloo, ending in 2018, and has been at the London School of Economics, I think ever since. So please tell us about integer lattices.
All right. Well, thank you very much, Sam. I actually don't recognize a lot of you. So it's nice to see there are a lot of new faces. It's nice to see that the department is evolving and see some familiar faces. That's, of course, also nice to see. Right. So I'll be talking about strongly connected orientations and their connection to integer lattices. It's based on joint work with Gerard Cornejols and Sioi Leo and Ola Silena, who are both PhD students at CMU along with Gerard. Ola actually did her undergrad here at Waterloo, so there's another Waterloo connection here. Right, so the goal for my talk today is quite simple. I'm just gonna tell you one theorem that we've shown, and I'll try to motivate why that theorem was interesting to us. It might be interesting to you as well, and show you some connections that maybe you didn't know or did know. So. Right. So to get started, I'll just tell you, give you the premise. So we have a digraph D on vertex set V and arc set A. Hopefully, I don't need to define what that is. I'll assume that the underlying undirected graph is 2-edge connected. So I'll assume this throughout the talk. The key object that I'll need for a talk is a notion that you've seen before. I'm sure if you've worked with digraphs, but the terminology might be new, and that's that of a strengthening set. So strengthening set is a set of arcs, so is a subset of arcs of the graph. Such that if you reverse the orientation of those arcs, the digraph becomes strongly connected. So such that, so how do I, so I say delete S and then add the inverse of S. If this thing is strongly connected, and I'll show you guys a picture. Strongly connected just means that you can get from any vertex to any other vertex via a directed path. So, so let's, for example, if I look at, so let me see how exactly I want to orient this. Right. So this is one example I want to keep on the board, and this is another one. Right. Let's see. Right. The printout here that I have is black and white. I need colors here. So. Right. So over here, if you look at this, you have the underlying undirected graph is just a 5-cycle. But what you have is not a directed 5-cycle. So to make it strongly connected, I need to turn into a directed 5-cycle. So you could do that by either, yeah, right, you go. So for example, this, if you flip these two guys, you'll get a strengthening set. So that's a strengthening set. Another one would be the complement of that in this example. This is also a strengthening set. And for this one, let's see. So if I, for example, look at this one, right? So if I flip this one, I'm creating a directed cycle. So these two vertices will be in the same strong component. And then what do I have here? I can go down, I can go up. And then if I flip these two, I could close the loop. So it's also strongly connected. There are other things as well. I won't explain why they're strong. They're strengthening sets, but if you're bored with my talk, you could just, I guess, convince yourself why they are. But yeah, so each color set is a strengthening set, right? So there's a there are a few deep connections actually to CNO about strengthening sets. So one connection is a theorem of Edmonds and Giles. 78, and the Edmonds-Giles theorem actually gives a convex Hall description or polyhedral description for all strengthening sets in a directed graph. So more precisely, what it says is that the convex Hall of the incidence vectors of strengthening sets. So I'll denote that by one subscript S. This is a 0, 1 vector indexed in dimension A. You have a 1 whenever you're using that arc, otherwise you put a 0. So we know exactly what this convex Hall is. This is so let me call this SCR of D for strongly connected reorientation of D. So to describe this, let's first focus on the 0, 1 hypercube, the unit hypercube. Then within that, what we'll do is we're going to have I'll explain this terminology, x of delta plus u minus x of delta minus u. This terminology, or this notation will be familiar to you if you've taken network flows. This is greater than or equal to 1 minus delta minus u for all subsets of u, proper subsets of u that's non-empty. So let me explain what this inequality is saying. Right. So first off, x of delta plus u, what that means is you're just looking at the arcs that appear in delta plus u, and you're summing the corresponding variables here. So where is this thing coming from? If you look at outgoing, it's outgoing. So for example, what it's saying is, like, if I look at, so you take a proper subset of the vertices that's non-empty. And what that inequality effectively is saying is that after you flip the arcs, you want at least one arc to leave the set or enter the set. I always mix the two things up. So it would be easier actually to see this if you rewrite this. So I could actually rewrite this inequality. So this inequality equivalently is saying the sum of xa, a in delta plus u, plus the sum of 1 minus xa, a in, maybe I'll use a different one, b in delta minus u is greater than or equal to 1. So it can be that all of these are 0 and all of these are 1. And that only happens if after you flip it, you have only incoming arcs. That's basically what it's saying. Right. So these are like the most natural inequalities one can come up with. If you want strong connectivity, you want to make sure that you, after flipping the arcs, you're able to actually leave any non-empty proper subset of the vertices. And that's exactly what the inequalities say. And it's just pure magic that this fully describes the convex hull, in the sense that if you put down these inequalities and intersect it with the box, you do not create fractional vertices, right? So you get a polyhedron where every vertex is integral, is 0, 1, and from there it's very easy to see that it must be a strengthening set. Right, so that's so what Edmonds and Giles proved is more general. What you're seeing here is a so-called supermodular flow system, and what they showed is that supermodular flow systems or submodular flow systems are so-called box TDI, which has this as an implication, but this was one of their key consequences in the work, actually. They mentioned this consequence in their paper, and it was a key motivation. Maybe I'm rephrasing things, but this really was a key motivation. And what we do in this work is we study some faces of this polyhedron. So I'll tell you our key theorem. And right, ACLS 25. So it's the extended abstract of it is appearing at IPCO this year. Right. Our statement is a statement about the integer points that sit inside so-called slanted faces of the polyhedron, and we actually look at integer lattice theoretic properties of these points. To unravel that, first let me move to a face of the polyhedron. To move to a face, I need to set some of these inequalities to equality. So I'll first tell you what those inequalities are. So let script f be a family of non-empty proper subsets of the vertex set. I need one condition. I want to make sure that those inequalities that I'm looking at, if I look at the right-hand side values, their GCD is 1. So their greatest common denominator is 1. This condition, we could drop it, but we have to rephrase the statement of the conclusion. But I'll just keep it as this. It's fine. So I want this GCD to be 1. This is the greatest common divisor. Right. And then what I'll do is I'll move to the corresponding face. And let F be SCR of D intersected with basically x of delta plus u minus x of delta minus u equals 1 minus u. So I'm moving to a face here. Right. Then let's look at the 0, 1 points that sit inside that face. So 0, 1 points are integer points. They're the same thing here. This thing contains, is this too low for you guys? Yeah, it's good? Okay. So then this contains an integral basis for the linear hull. For the linear hull of F. Which I'll refer to as a len of F. So what do I mean by an integral basis? Right, so what do I mean by an integral basis? It's just a basis so that whenever you have an integral vector in the linear hall, you look at the unique description by the basis, the coefficients are all integral. So that's what this is saying. So i.e., B is a linear basis. So this is in the linear algebraic sense, linear basis, and every integral vector, vector in the linear hall of B or F, whichever, they're the same thing now, any integral vector in here is an integer linear combination of B. So the coefficients are all integral. All right. So this is the key theorem. So basically, the gist of it is I have a polytope, an integral polytope. I'm looking at a certain face of that polytope, the integer points in there, and I'm just I'm saying that the integer points there contain an integral basis for the linear hall of that face. This is a lattice theoretic statement for those of you familiar with integer lattices, because this equivalently is saying two things. So equivalently, so first off, what it's saying is that if I look at if I look at the linear hall of F and intersect it with all the integers, this is going to be an integer lattice. It's actually the densest possible integer lattice that I can come up with inside the linear hall. This is equal to the lattice that is generated by the integer points in here. So it's equal to the lattice generated by the integer points in A. Okay? So the lattice generated by this is looking at all the integer linear combinations here. So for example, if you look at numbers 2 and 3, the lattice that they generate is basically all of the integers. Right. But it's also saying a second statement that's going a step further than this. It's saying that the lattice itself, every lattice, integer lattice, has a basis, very much like what happens in linear algebra, has a basis, and it's saying that actually your generating set contains a basis. And now there's a key difference between what's happening in linear algebra and integer lattices. This is not true in lattices in general. So lattice of F intersect ZA contains a basis, a lattice basis. I'll write down lattice basis so that's clear. A lattice basis inside the generators. And this might be a bit bit of an obvious statement if you think about it from a linear algebraic perspective, but for integer lattices, this is actually not true in general. Like for example, if you look at the lattice generated by the numbers 2 and 3, this is going to give you all the integers, Z. But the only basis that generates Z is 1 or minus 1, and that's not contained among the generators. So this statement in general is not is far from obvious. And so that was for the second example. And this one as well, if you look at the lattice generated by 2 and 4, this is all the even integers. It's 2Z. And it's not the same thing as the linear hall of 2 and 4 intersected with the integers. So these are two examples that show that either of these two things in general could go wrong. Right, so this is just a brief, the connection to integer lattices. So this is the theorem that I'll show. But actually, I'll tell you, let me motivate it and give you an application before going a step further. Are there any questions so far? Right, okay. So if I'm going too slowly, please let me know.
I have a question.
Yeah.
So what happens to if we consider the inequalities of like between 0 and 1? Like,
Then this statement is not true. Right, yeah, so I'm saying a statement about some faces of F, some faces of this polytope, but not all faces. Actually, I'm looking at sort of faces, slanted faces. So these are faces that are not contained in x equals 0, x equals 1. So they're diagonal faces. And there is a reason for that. If you look at the other faces, this statement is not true. At the end, I'll state a conjecture about those ones. But yeah, that's a very good question. Yeah, so that's not true. So let me tell you a bit about the motivation, because this is this needs context. Otherwise, it's just a weird theorem. Right. So let me tell you about one other object that is very relevant when you're looking at strong connectivity. So if you look at a digraph, the key obstruction to strong connectivity are cuts where all the arcs are going in the same direction. These are things I call die cuts, and some other people also call die cuts. So die cut is a subset of the arcs of the form delta plus u, such that delta minus u is empty. Okay, and here I'm assuming u is not the empty set or v. So if you look at this example over here, so these things are not strongly connected. So the examples that yeah. So this thing that you're seeing here is not strongly connected. And one reason why it's not strongly connected is because I have cuts where all the arcs are going the same way. Right? If you look at this, the arcs are all going out. Nothing's coming in. And to get a strengthening set, you need to make sure that you get rid, after flipping the arcs, you get rid of all of these, which is effectively what this thing is doing. All these inequalities are doing. Right, so now there's an unpublished conjecture by Scriver about these. So if you give me, so this appears in some notes of his on his webpage. Right, so let's look at the, so we're working with digraphs that are not strongly connected. So I'm going to look at all these die cuts, and I'll look at the smallest die cut I can get. So let's tau be the smallest size of a die cut. Right, in that example, it's 2. I can't get anything smaller. Then, so what you'll notice there is that, and what this is effectively saying is that if I, for every die cut, there's at least one arc in the die cut that I need to flip in a strengthening set. So so if I want to, so the conjecture says that then A can be partitioned into tau strengthening sets. Right. And partitioning here is key. So first off, why is this tau relevant? I can't partition it into any larger number of strengthening sets because every distinct strengthening set is going to intersect my smallest die cut in a different edge. Partitioning here is key in the sense that this is not really a packing problem. I'm not looking for disjoint strengthening sets. I'm looking for strengthening sets that partition the arcs. And you could see this by just noticing that if you have a strengthening set, anything larger is not necessarily a strengthening set, right? If your digraph is not strongly connected, the entire arc set is not a strengthening set, yet you could have smaller strengthening sets. So here, this partitioning is really key. It's not, this is a true partitioning problem. It's not a packing problem. Right, so there's this conjecture, and what this lattice theoretic result does is that it proves this conjecture if you allow subtraction. That's what it's doing. So let me clarify what I mean by allowing subtraction. So so what I'll do is I'll actually focus on the minimum size die cuts, okay? And that will be my, my family F. All right, so these are going to be all the subsets U, such that delta plus U is tau and delta minus U is empty. All right, and what I'll do is when I'm looking at this partitioning problem, I could just focus on those strengthening sets that intersect each one of these die cuts exactly once. They have to flip exactly one edge on these things. So I'll just focus on those. So these are, I'll call this script C. So these are all strengthening sets such that S intersect delta plus U is exactly 1 for every U in script C. Just focus on those. Right. Then, what do I have? Then what I argue is that I can decompose the all ones vector. Okay, so this is the all ones vector for the arcs into an integer linear combination of things in here. So lambda S, 1S. S in script C, and each lambda S that I'm choosing is an integer.
Every U in F, the strengthening set that you're picking?
Yes, thank you for the correction. So this is right. Then this has a solution, or is feasible. This is feasible. Right. This conjecture is saying that if you impose additionally that these are non-negative, that this is a feasible system. Right. So why is this a consequence of that? Well, what do? You just move to the corresponding face of the SCR polytope, right? If you move to the corresponding face, I set all of these to equality, then what is this set that I'm looking at? This is just making sure that it's satisfying those inequalities as equality. So these are precisely the strengthening sets that are sitting on that face. And then why is this true is because some lattice theoretic thing. So let F be the corresponding face, be the corresponding face of the SCR polytope. Okay, then the key thing here is F intersect ZA is precisely the incidence vectors of these strengthening sets. The intersection being 1 means that after flipping the arcs, you have exactly one outgoing arc, basically. That's what's going on there. So this is the case. So what this is saying now is, right, so now what we know is that this thing has a, if I look at the integer lattice generated by the points in here, it's the densest possible lattice in its linear whole, right? So to make sure that the all ones vector is in that lattice, all I need to make sure that is that the all ones vector is in the linear whole. That's it. So then, so there's a fact here I'm not going to tell you. We know that the all ones vector A belongs to the linear whole of F. So this I won't tell you, but this requires a proof. But this is something that is known. The reason why this is true is, in fact, you could express the all ones vector here as a conic combination of these vectors. This is a known fact. In fact, it's not just in the linear whole, it's in the cone generated by this. So I'm not explaining this, but I don't want to focus on that. But what we know is, well, this is also an integral vector, right? So what that implies is that the all ones vector also belongs to the lattice generated by F intersected with the integers. Right? Because the linear whole of F intersected with the integers is the same as the lattice. And what this says is precisely this statement, that this system is feasible. You could express it as an integer linear combination, and this finishes the proof. Right? So actually, in fact, this theorem is proving a lot more than the feasibility of the system. This is actually saying that among these strengthening sets, you could actually find a lattice basis for the lattice generated for lin of F intersected with ZA. But anyway, so that's the so that's one corollary of this result. I'll give you another. So I'll start moving towards explaining what goes on in the proof of this. But are there any questions before I do that? Right. I can't tell if what I'm saying is either too obvious or too difficult. So it's one or the other. It's yeah. F is the corresponding face of SCRD. So F is the face of the SCR polytope corresponding to this. So you're setting the corresponding constraints to equality. So it's the same relationship that I have here between F and script F. It's just this. Yeah. Yeah. Joseph, you had... that was it? Okay. Yeah. I'm trying to save time by not writing everything, but yeah. So let me. So actually, to motivate what goes on in the proof, I'll give you a bit more of the backstory of this. Yes.
Sorry, I have a question. Is tau based possible if you relax the problem this way?
Come again, sorry.
So tau is based possible for Schreiber's conjecture. Right.
You get different statements for different taus. So here, instead of working with, I could have worked with a smaller tau than this, right? And you get a different conjecture. It's very weird. It's a very straight, that's an incomparable statement. So I could have, if the minimum size of DECA was 10, this is saying find a partitioning into 10 strengthening sets. But actually, there's also, if this statement is true for all digraphs, I could also get a statement for, I could give you 5 strengthening sets that partition the arc set. But that's a different, for specific digraph, it's an incomparable statement. For all digraphs, they're equivalent. It's a little strange, but I'm not getting into the nuances of this. It's a little, it gets
You can't go above.
I cannot go above, exactly.
The original question was, over here, can you go above?
No, you cannot, because you're here, you're also packing, right? You're finding tau disjoint strengthening sets, and each one of them needs to pick something from your die cut, from your smallest die cut.
But here you're not packing, so could you hope for a higher number there?
Oh, I see. Well, the way I've set it up, it's going to be exactly tau. Like, I don't even need to say it's actually, I haven't, over here, you'll notice that I didn't say 1 transpose, the sum of lambda is tau, because it's implied. I actually forgot to write that, but it's implied. This is implied. 1 transpose lambda is tau is implied. I did not write this, but this is implied from this. Yeah.
And if you change that tau to like tau plus 1, like this would not work.
If I change that tau to tau plus 1, I cannot argue that the all ones vector is in there. But if you, for whatever reason, you know it's in there, it will imply it, yeah. So if you can satisfy this fractionally, you can satisfy it integrally. That's what it's saying. Yeah. Very good question, yeah. Right. Right, so I'll tell you a bit more of the backstory, which is my segue into the what goes in the proof. So I told you the theorem. I told you about Scriver's conjecture. I'll tell you about something that you may have heard of, Woodall's conjecture. To talk about this, I need to tell you yet one more thing, which is so it's the die join. So a die join, this is a very weird object. So it's a subset of the arcs, such that, so there's 2 ways of defining it, but is a subset that intersects every die cut at least once. Cut at least once. Or I'll just say intersects every die cut. Right, so it's a blocking object, okay? There's another way of defining this, which allows you to relate it to strengthening, strengthening set. It's saying that these are a set of arcs so that if you bidirect them, the digraph becomes strongly connected. So D union J inverse is strongly connected. These 2 concepts are equivalent. These 2 definitions are equivalent over here. Right. But what this allows you to show is that if you're a die join, you're a strengthening set. Okay? If your network becomes strongly connected after bidirecting a bunch of roads, one-way roads, the other way around, sorry. If your network becomes strongly connected after flipping the orientation of a bunch of roads, it's going to be strongly connected after bidirecting them. So, to relate it back to that, it's if you're a strengthening set, you're a die join. Right? If this is strongly connected, if I add S back to it, it's going to remain strongly connected. Right. The converse is not true. And actually, there's a very simple explanation for it. The entire arc set is always a die join. But the entire arc set is not necessarily a strengthening set because your digraph may not be a strongly connected. So and more generally, if you have a die join, anything larger than your die join, anything that contains your die join is also a die join. And that relationship that feature is not, does not hold for strengthening sets. So strengthening sets are more delicate, die joins are a bit coarser. Right, and just like we have a description for maybe over here I won't try to give an example here. Every strengthening set is a die joint, so I think you already have an example there. So, right. Just like this theorem, there is also a theorem that gives a description for die joints of a digraph, except that because of this up-comprehensive nature of die joints, our description is going to be for the up monotone closure of this. So, so the theorem again, so this I'll attribute it jointly to Edmonds and Giles, the same paper, but also to Lucchesi and Younger, another Waterloo connection. Which says that we could actually give a perfect description for die joints. So what is a description? You're looking now not at the 0, 1 box, but the non-negative orthant. This time what we're going to ask is that we're going to ask that we intersect every die cut at least once. So x of b greater than or equal to 1 for every die cut b. Right. So you could see that for 0, 1 vectors, this is precisely the die joint by definition. And actually, that's all that you get here. This is an integral polyhedron. And the vertices are precisely the incidence vectors of inclusion-wise minimal die joints. So that's so right. So we have the analog of this for die joints as well, and we also have an analog of Scriver's conjecture for die joints. This one is published and is from the same year. I don't know if this is 78. I might be wrong, but it sounds right. But anyway, it says that D has tau disjoint die joints. So tau is the minimum size of a die cut. Right, so this is asking for tau disjoint die joints now. If you have tau disjoint die joints, you also get a partitioning into tau die joints, just because anything larger than a die joint is also a die joint. But I've written it in this way because that's a partitioning problem. This is really a packing problem. They're inherently different problems. Right. Okay, so one thing to note here is that if that conjecture is true, this conjecture is true. Because if you can partition your arcs into tau strengthening sets, every strengthening set is a die joint, so you get a partitioning into tau die joints, and then you could, so then you get this. So that's an obvious statement. So Scriver, I'll just say Scriver for D, for sure, implies Woodall for D. Right. But The converse for the same digraph is not obvious at all, and I don't know if that converse is true. I mean, if both conjectures are true, they're equivalent, presumably. But it's possible that for a digraph, one is false and the other is true. The converse for some digraph is, I don't know how to prove it. But what I can show is that if I can cook up an instance, a different instance D prime, and argue that if Woodall holds for that cooked up instance, then Scriver holds for this instance. So I'll explain that. Yeah, not sure how much time I have left. I'll try to wrap up quickly. So consider the following operation. So I'll try. So this is I won't spend any more brain power on this. But now consider the following operation. Operation on the digraph. So what I'll do is for every arc in your digraph, what I'll do is I'll introduce a middle vertex. Let's call this A. I'll introduce a middle vertex. I'll call that TA. The original arc is going to go here. Okay. Then what I'll do is I'll introduce tau minus 1 flip arcs. So that is what I'll do. And I will do this for every arc. For each A in A, we'll do this. This will give us a new digraph, which I'll call, so this is D prime. Okay, and what I'm going to do is I'm going to map strengthening sets to dijoins here. So if you give me any arbitrary strengthening set in this digraph here, I'll define a J here, a corresponding J. So phi of S, but I'll just call it J, where if you used this arc in your well, so I'll say, if you used A in your strengthening set, then A will be in your dijoin here. Otherwise, if A wasn't in the strengthening set, then the flip arc over here, I'll call these are A bar. Let's call them A bar. This is A. Then you just give it one of the A bars. Right, so through this, so what I claim is that if I do this, strengthening sets get mapped to dijoins. So what does a strengthening set do? A strengthening set here is just, if A is in there, it's just flipping the direction. Right, so if it's just flipping the direction here, if I'm using it here, over here has the same impact as bidirecting this. Because if you bidirect this, these two nodes become the same, and you're just ending up with essentially the same instances here. It's just going back, that's it. Whereas if you don't use the arc here, I'm giving it one of these arcs, and I'm saying bidirect that. If you bidirect it, these two arcs, these two vertices become the same, and then you're just back to where you started from. Another key feature that the dijoins here have is that the dijoins here are using precisely one vertex, one edge incident to this middle vertex. So I'm looking at dijoins that are intersecting this vertex exactly once. Another feature the digraph has on this side is that it's a bipartite graph. The new vertices I introduced are all sinks. The original vertices all became sources. So what I've done effectively is I've moved from the digraph to a bipartite graph, where every sink has degree tau. And the interesting dijoins are those with exactly one edge incident to them. So they're special perfect B matchings, if you will, in bipartite graphs. So that's what this transformation does. But one thing now that this implies is that if Woodall holds, so Woodall for D prime implies Scriver for D. Just to close the loop here, because if you can find tau disjoint dijoins in this digraph, this vertex itself is a die-cut of degree tau. So the dijoint that you're looking at will have exactly one edge incident to this. So then that J is phi of S for some particular S. You map it back. And so that, therefore, your packing over here, you could argue, corresponds to partitioning and to strengthening sets here. So that's really the proof was in the construction and the right way of looking at it. I'm just going to write down here more explicitly. So it's a dijoint. So if this is strengthening, if this is a strengthening set, then this thing is a dijoint such that J intersect delta minus TA is 1 for every TA, for every sink TA. So that's what's happening. And so let me move towards the end. So I'll refer to a pair D script F. So a pair DF is a digraph. This D over here is really that D prime here. Maybe I'll include that here so that it's, I'll just stick to that. This is the end of that story. So if D is a bipartite digraph, so by bipartite digraph, I mean a digraph where every vertex is a source or a sink. So all the cuts that I put in here are die cuts. If U is in here, then delta minus U is empty. I want to make sure that all the sinks are also in there. So what's going on here, I'm trying to map Scriver's, like our original setting, the SCR setting, to this setting. So this script F is telling me which face to move to. So this is saying that the complement of every sink is also an F. So is F for every sink V. And one last thing that I need is that the corresponding face of the dijoint polytope is non-empty. So I look at the dijoint polytope, and I move to the face dictated by script F. So X of delta plus U is 1 for every U in F. Right. So basically what's going on is to prove my theorem, or our theorem, what we do is we do this transformation to get to this digraph D prime, which is a bipartite digraph. And through this transformation, the family script F that I had originally that told me which face to move to gets mapped to a family of die cuts, which includes, I'm going to actually force it to include all the sinks. And then I get things mapped to this corresponding face of the dijoint polyhedron. So I want this to be non-empty. I didn't need to do this before, but now I actually did need to do it before. But then what we prove is the following, and so let's call this F. What we prove is that F intersected ZA contains an integral basis. For the linear hull of F. And just a couple of words about how the proof works. So here we're dealing with bipartite graphs, and we're dealing with dijoins that intersect all the sinks exactly once. So there's some sort of like perfect B matchings. The way the proof works is inductive. We first focus on certain faces of this polytope. Actually, we focus on the facets, and we look at facets that come from non-trivial die cuts with at least 2 vertices on both sides. And then we do some decomposition, which is fairly routine, and it's done typically in the context of perfect matchings and matching theory. So we do this, and at the end of this process, we end up with some basic instances. So these are some basic bipartite graphs that we end up with. If this bipartite graph ends up having the same number of vertices on both sides, then we're dealing precisely with perfect matchings. And in that case, the result here follows from known results in matching theory. But if the bipartite graph that you have is skewed in the sense that it has fewer sources than sinks, then that's where you get a new theory akin to the theory of bricks in matching theory. And so then to deal with those basic objects, you need to rely on results from the exchange axiom for M-convex sets. So what we do is we map basically dijoins end up being, so one side of the story is that they're perfect B matchings. Another side that I didn't talk to you about is there is some matrix optimization going on the vertices. It turns out that if you keep track of the degree sequences, they're coming from the intersection of two polymatroids, basically. And then there's a certain exchange axiom that holds for these things, and that allows us to basically resolve the case for the basic instances. There's also another side I didn't tell you about, which is about Hilbert bases. We use those for the basic instances, but right, yeah. It's too much going on here. Which is why I just opted for board talk. So, right, I think I'll stop there. Yeah, thank you.
Thank you. Any questions? I actually have a question then. I'm still a little hung up on this board, and especially that the set script C is even non-empty. It seems to me when I was trying to work this out, you were using this two-connectivity or this two-edge connectivity.
Right, right. It is using it to yeah. So actually, yeah. So if you don't have two-edge connectivity, you can't even find a strengthening set. So two-edge connectivity is required to guarantee the existence of a strengthening set. There's a basic a non-trivial theorem and directed graphs. Actually, I should have mentioned at the very start. If you have a two-edge connected graph, there's a strong orientation. Yeah, you can come up with a strong orientation of any two-edge connected graph, and that's why this set, the definition I gave actually makes sense. I should have mentioned that right off the bat. So strengthening sets do exist. Actually, I didn't. So strengthening sets do exist in general. And then why does this thing exist? Yeah, that's basically hidden in the why here that I didn't explain. But yeah, there's things I didn't explain. Yeah, but that's a very good question. Yeah.
Does anything interesting happen in the case where the graph's already strongly connected?
So actually the statement I could have stated everything in terms of undirected graphs. The starting orientation for the statement, the original statement that I gave, is irrelevant. You could reorient the graph. The SCR polytope is not going to change. It's just you're just looking at a twisting of it or switching of it. So it doesn't. Although there are some non-trivial things going on. If you take a face and look at the linear hull of that face and apply the theorem to that, that's one theorem. But then if you take the same face and you switch it and you apply the result again, you're getting a different theorem actually. So, but because the theorem is applied for all different faces, they end up being the same. But for even a specific face after switching, you're getting a different statement. So I haven't explored that really. It's there's a lot of strange things happening here. Yeah, yeah.
Other questions? Okay, that's
Well,
it.
thank you.
Thank you, Ahmed, again.
Thank you.